we're going back to our thrust now. So hopefully you've started trying to draw your thrust on your line of section. I hope you used a very thin pencil. And I wanted to think about like the angle between the beds and the thrust themselves. So one of the things that I'm thinking about in particular is when you look at the thrust, you can see that very often it's the same rock unit that is along the thrust. Okay, there's some changes, but most of the time, like you can see that here, and for example, the EEL tends to be along the most of the thrust that are at the front here. If we look at this one, it's essentially that MET here. If we look at this one, we've got a DPA. So we seem to have a situation where the rock type along the thrust is very similar, is very consistent for long distances. Again, 1 centimeter is 500 meters, so we're talking about along kilometers, like even tens of kilometers. It's the same rock type along the thrust fold. If we had a situation where the thrust was very oblique to the beds, like in this case, for example, you can imagine that, okay, so if you've got erosion on different level, let's say this is the topography here. So this is the surface of the mountain. You can see that here the thrust will be in contact with rock 1. So 2, 3. So here, if you look at on the map, you will have the thrust, and then it will be rock 1 directly above the thrust. If you erode a bit more, so if you're going a bit further in distance, you know, you may have a bit more erosion in other places, and then you will end up in a situation where, again, this time you've got the thrust, but it's rock 2, which is now just above the thrust. So you can see that how, if you've got beds that are very oblique to the thrust, if this is the erosion in another place, again, in this case, rock number 3 is going to be just above the thrust. So if the thrust is very oblique on the beds, you end up with, on the map, you're going to have a lot of variation in the rock type that is exposed along the thrust. Now, what would happen if we had a situation like that, where our thrust is like that? This is our topography. And in this case, what we have is something like that. So the thrust itself is sort of rooted into the same rock type. So let's say that we've got rock number 1, 2, 3. And in this case, we've got that thrust is sort of following its rooting itself in the same rock type. You can see that here in that situation, whatever the topography, even if you erode here, so in that case, you know, rock 3 is above the thrust. You erode more, rock 3 is still above the thrust. You erode more, again, just above the thrust, we still have rock 3. So in this situation, you end up in if you've got something like that, you end up with the same rock type exposed along the thrust or along the strike, whatever the difference in elevation along the thrust. And this is probably what we have in this area. We talked about that in the lectures, like about what happens in the Alps, and we talked about this décollement. Florian talked about the décollement, and in that case, in the Alps, the décollement was the Triassic. All the thrust faults tend to root themselves in the Triassic, and you had a sort of, we talked about thin skin tectonic, where we have a situation where all the thrusts are going to, let's say this is our topography, and all the thrust will tend to connect to a similar level here. So what you end up doing is essentially repeating the succession like that. So again, that rock unit is going to come like that. So you can see that here we've got, I'm going to change the order, so we're going to say that the bottom one is rock 1, and then we've got 2, 3, 4, 2, 3, 4, 5, 2, 3, and you can see that in that case we've got the thrust, it's rooted in unit 1, and then we've got 2, 3, 4, and we've got another thrust rooted in rock 1, 2, 3, 4, 5, and then another thrust, rock 1, 2, 3, 4, and so on. So we've got this repetition of the succession, and this is this décollement. It's a French word, so décollement. And in the Alps, we talked about that Triassic evaporite layer, which facilitate which can be easily deformed, so all of the thrust tend to connect to that décollement. So underneath, you've got very minor deformation. Above that, you get all these slivers of sedimentary rocks that are stacked on top of each other. So this is very likely what we have here. One thing to note is that in that situation, there's no clear décollement level. In here, it tends to be the EEL rock, which is, what is it? Massive limestone, dolomite mottled, dolomitized equivalent. So I guess there may be some evaporite here, which may lead to localization of deformation. Here we've got DPA. DPA seems to be used in a few places. DPA Palliser formation. Again, dolomitic limestone. So again, there may be processes that lead to localization of deformation in these particular units, but it's interesting to note that we may have different décollement level. So if we are in this situation, you can see that the thrust, the dip of the bed is going to control, if you've got the dip of the bed, it's going to control the dip of the thrust. You may have an angle at the bottom, but overall, like your thrust will not be, you won't be able to draw thrust with with an angle which is much more different from the beds next to which it is. So I'd like you to start thinking about your cross section here. Think about the dip of this thrust compared to these ones, and then these ones, and think about the dip of the beds in this area. One of the big difficulty in that cross section is to keep the thickness of the bed constant across the section. This is something you're going to really struggle with, and hopefully you will manage. But the DPA here must have the same thickness than the DPA here. The MBFL here must have the same thickness than the MBFL here and MBFL here. So that will be the greatest difficulty, but otherwise it should be perfectly achievable. So off you go.